In 2022, Chris joined the Rocky Mountain Institute's Embodied Carbon Initiative, and within the Rocky Mountain Institute's initiative, he joined the carbon-free building team. There, he leads the effort on Home Builders Can, which is a unique community of practice for home builders working to decarbonize. He also worked on the development of the ResNet ANSI Standard 1550 for the measurement and reporting of embodied carbon in homes. In 2019, he helped to establish the Builders for Climate Action and has been leading the development of the BEAM carbon estimator tool for low-rise construction. At the Builders for Climate Action, he co-authored 4 major studies on embodied carbon in home building. From 2011 to 2022, he was the director and teacher at the Endeavour Center, a not-for-profit sustainable building school. Prior to that, he ran a design-build firm specializing in carbon storing, healthy, energy-efficient new construction and renovations. He's authored 7 books on sustainable building, and his latest book, Building Beyond Zero, New Ideas for Carbon-Smart Architecture, is co-authored with Bruce King and published by Island Press. Chris, welcome.
Thanks. Yeah. Okay, well, thanks, Heather. Thanks to everybody for showing up here today and to Canon for inviting me. Hello to everybody who is tuning in online. I'm really excited to be able to give this presentation to you today. The general thesis here is that we can actually transform buildings from emitters of carbon to storers of carbon. And I'll sort of go through a bit of the theory of how we can do that and also look at some case studies. As Heather mentioned, my background is in residential and small commercial design build. And I say that I'm an accidental embodied carbon nerd. And I am one of those because in, must have been 2011 or 2012, my daughter at the time was sort of a young teen, and she was having one of those moments of climate anxiety, like a lot of young people did then and still do now. And she sort of said to me, you know, hey, Dad, I know you do this green building stuff. You know, I think you're doing something for the climate. Are you doing something for the climate? And if so, like what? And is it enough? And so anyway, it was like a really important moment for me because I wasn't aware of how much stress she was feeling about it. And so I felt like I had a 2-part answer for her. The first part was, yes, I'm doing everything that I know how to do to make the buildings that I'm designing and building operationally as good for the climate as they can. We had been doing net zero energy buildings for quite a while at that point. We had been using renewable energy systems. So I felt really confident that I could say to her, like, yes, you know, this, I'm doing good in this, you know, or everything I can for you. But I had literally just started working on this book called Making Better Buildings. And it was an attempt, again, for the residential market to sort of help people think about all the different criteria that might be considered, you know, green, and figure out how to sort of weigh that up. And it was kind of bugging me as I was doing the research that I didn't know the carbon footprint of all these different materials that were going into the book, and I didn't have an answer from my daughter Emma about the carbon footprint of the materials in the buildings I was making. And so I kind of started to try to do a dive into the embodied carbon of building materials. And so, you know, every material that we use or we listed in Making Better Buildings, we actually found whatever data we could at the time. There wasn't a lot in 2011, 2012 on embodied carbon, but, you know, wanted to attach that to the materials. So readers had a good sense of that, but it helped me develop a really good sense of it too. And so, you know, once you start going down that rabbit hole, you realize, oh, there's way more to the life cycle than I had initially been thinking. You know, I had this focus on energy efficiency, and then, you know, you sort of, you open up and see that, oh, the harvesting of the raw materials for building products, the manufacturing of them, the transportation of them, like all of these things add emissions, and way more than I ever imagined when I first started looking into it. And I'm sure, you know, this has probably been coming up on your radar too, the fact that, the embodied carbon of a new building like the one we're standing in can be like half a ton per square meter of floor area. And so, when you're trying to look your daughter in the eye and go, yeah, here's what I'm doing for the climate, if I'm making buildings where there's a half a ton of emissions for every, square meter of floor area, I'm clearly not doing everything I can for her. So that kind of started my deep dive into this. And so since then, I've been looking at, how do you count this? What's the data that we're using to do this counting? What does it all add up to? And so last year, my colleagues at RMI and I attempted to do a sort of back of the envelope, how big are, embodied carbon emissions? This is in the US, roughly 370 million tons of emissions every year from the materials that go into making buildings for the US market. That's sort of residential and commercial, put together. And so we kind of came up with this number, which to me sounded big, but I didn't know if it was big. So what I did was I looked at, well, how much do whole countries emit? And you can see here, like the emissions from building materials in the US is the equivalent of the entire economies of South Africa, Australia, Vietnam, Italy. So that's everything that they do there, all the cars they drive, the buildings they make, the things they heat, is building materials in the US market is somewhere in the neighborhood of that. So it's, not only the little buildings that I was building, but all of us who make buildings are contributing to that. And so, I kind of, for myself, cast my mind, back to, okay, when I was trying to tackle operational emissions, what were the strategies? You make the buildings really energy efficient. You try to get the energy needs as low as you can, and then you provide the remaining energy with renewables. That's the formula, because you can't necessarily get rid of all the emissions. We are attached to power grids that still make emissions, but you sort of try to offset those emissions with renewables. And so it turns out you can do the same thing on the building materials side, because we can use products that actually store carbon in them, and I'm going to get into what those are and where they come from, but in the same way. So you want to reduce the embodied carbon of all of the parts of the building that you can, every component reduce, and then try to use as many carbon storing materials as possible to try to net out at zero, or in fact even go beyond that and store more carbon than was emitted. So this is kind of our little mantra within our RMI team now. It's sort of like substitute and store. Those are the two things that we can do. We can, there is no version of carbon storing concrete right now, but you can use the lowest carbon, footprint concrete that you can get, and then maybe carbon storage in the carpet or in the dividing walls or in the insulation or some other parts of the building. So for a while, my focus on these bio-based building materials that store carbon, it made sense. My own construction practice, we did a lot of straw bale construction, hempcrete construction. I was already using a lot of bio-based materials. It's been a bit of a weird and long trajectory trying to sort of make the case for carbon storing materials, for bio-based materials. Just recently, this report from the United Nations came out that I was thrilled to read, because it read like I wrote it, but I didn't. Some really respected researchers and scientists wrote it, basically starting to realize, like, oh, the only way that we get building embodied carbon, down to zero is to use carbon storing materials, and bio-based materials are the most commonly available right now. So this is a very quick case study. I'm going to show you some more case studies, but I'm going to use this one to try to cue a bunch of the questions that I have a feeling are starting to go through your head right now as I'm talking. So this was the last project that I worked on before going to Rocky Mountain Institute. It's a 5,000 square foot classroom at Trent University up in Peterborough. And the university really wanted to achieve the ILFI's zero carbon certification on this building. So, hence you can see there's lots of PV on the roof. So, again, the team had a pretty good sense of what it took to make the building, zero carbon from an operations point of view. But they reached out to me to say, is there such thing as zero on the materials side? And I was like, I think we can get there, or get pretty close to there. And so I joined the design team with the express intent of trying to see if we could also get the embodied carbon of this building down to zero. So how we did was not quite zero, but it was really darn good. So, one of the great things about doing this project at the university is they have a very set building style that they use at the university. So we were able to model what they would have built if it wasn't for this project quite accurately, because they kind of do the same thing with every new building they do there. So that building, the base case on the left, would have had about 211 tons of emissions associated with the materials, or been about 498 kilograms per square meter. And the threshold for the ILFI program is 500. So the project actually would have met ILFI's needs for the zero carbon certification in its base case. But what we did, if you sort of scan down that as-built line, you'll see in some cases we took components of the building, like the foundation, and just did everything we could to use the lowest carbon materials possible. So, the footings and slabs and the foundation walls, you can see there were big reductions, but not reductions down to zero. But then you can see places like the exterior walls, the interior walls, those we used a lot of carbon storing materials, and we ended up reducing the embodied carbon of that building 88%. We got it from 500 kilograms per square meter down to 60. So, that was a pretty good attempt, and there are certainly other examples of the buildings that go further than that. So as soon as I start showing negative numbers, and as soon as you start looking at LCAs that have negative numbers, you get this. I took this slide from my colleagues at Building Transparency, who make the EC3 tool. This is very much what happens. You talk about carbon storage in building products, and all the LCA people, start fist fighting over, how do we count it? Should we count it? What's it worth? And so I'm going to kind of go through how it's counted now and sort of talk about how it can be valued. Weirdly, in life cycle assessment right now, there are actually 3 acceptable ways of dealing with carbon that might be stored in building products. So, like right off the bat, nobody ever gets the same answer, because the actual standards that govern how you calculate this say that you can either ignore it, like pretend it doesn't exist, because the theory is, well, it was a tree, it grew, we used it, another tree is going to grow, it all turns out to be even, so we just ignore it. The -1 +1 method says, well, you track the flow of the carbon. So some carbon came out of the atmosphere into a tree or a plant. You sort of put that into a building for a while, but then you assume at the end of its life, it's going to get fully re-emitted. And so it's kind of like ignoring it, because you're basically just showing a -1 here and a +1 there. And if you're looking at a whole life cycle, it comes out to 0. And then you can also look at a life cycle carbon flow, which is like the -1 +1, but it allows you to say, well, at the end of life, we don't necessarily have a 100% emission. If you put something in a landfill, some will get emitted, some will stay there, or there might be other ways of dealing with these products at the end. So it allows you to sort of tune what the end of life, or what you think the end of life will be. So the result of having 3 ways of doing this is that it's really hard to figure out what you're looking at. You might be comparing 2 products that both have, carbon storage involved in them, but if one ignored it and one did that number 3 option, you're not seeing the same number. So it's a pretty confusing landscape right now. So for myself, what I wanted to do was think about not just the carbon accounting version of this, but to me it was important, does putting carbon in buildings, what is the actual climate impact, not the sort of LCA numbers, but the climate impact. And so I sort of traced out, what does the life cycle of a biogenic product look like? And so, the line across the middle there is 0 emissions. And so when we plant a material, there's usually some emissions involved in it. You're driving a tractor on a field, or putting energy into growing seedlings or something like that. So there's usually a little burst of emissions. And then there's this period where that plant is pulling carbon dioxide out of the atmosphere. It's great. That's what plants do, right? They photosynthesize, they pull CO2 out of the atmosphere, They put the C into their body, they put the O back out in the atmosphere so we can breathe. So the whole time the plant is growing, it's taking carbon out of the atmosphere. There's less up there than when it started growing. The length of time of that drawdown could be, 2 months for wheat straw. It could be 60 years for a northern spruce tree. So, that the timeline there can be really different, but, all plants are drawing down carbon. And then if we're going to turn that plant material into a building product, there's all the life cycle stages. There's energy and emissions involved with harvesting it and manufacturing it and transporting it and building with it. But by and large, you end up with a product that by the time it gets into the building is still a net store of carbon. So there's less carbon in the atmosphere for whatever that building or product lifespan might be. It might be 10 years on a carpet. It might be 100 years on an insulation product. That also can vary. But the whole time the carbon is in the building, it's out of the atmosphere and sort of below the zero line. And then there's a whole bunch of things that could happen at the end of the lifespan of that product. It could be reused, which would be great. You'd continue to store the carbon and hardly add any more. It could be recycled. It could be turned into biochar. It could be turned into burn for combined heat and power. Or sort of, worst case, but also pretty typical scenario is it gets either, landfilled or incinerated at the end of its life, in which case there are some emissions again at the end of life. But that's kind of what the trajectory of a carbon storing product looks like. And then the trajectory of a non-carbon storing, a mineral-based product or a petrochemical-based product, is that red line. So all the same steps, but basically there's emissions at every point of the lifespan, and so that product's been responsible for emissions for the lifespan of the building. So if you do a really typical life cycle assessment of a building, despite those two very different kind of trajectories, what you do is compare kind of the answer at the end. So, whether it's whatever two products, there's often not a big difference between the carbon storing sort of biogenic option and the other options, because you're sort of looking at them at the end of their life, and you're typically using the worst case scenario for end of life for the biogenic one. And so you'd look and go, oh, there's only, X difference between these two things. But what's really going on, what the climate's really feeling, is this. Once you put emissions into the atmosphere for the product that's above the line, those emissions don't go away, right? They actually trap heat in the atmosphere, and then next year or tomorrow they trap more heat and more heat and more heat. So there's actually, that line in terms of how the climate feels, it should be, it goes up for quite a few hundred years before it starts to go back down. And the carbon storing product, similarly, that carbon has not been in the atmosphere for the whole lifespan of that product. And so there's a really big difference between the climate impacts and compared to just the sort of like the final answer that you get at the end of an LCA. And so, basically what we're doing is saying, okay, we're absorbing carbon dioxide. These are typically, short cycle plants. They would have either, come to the end of their life, they would have rotted, burned, been eaten, but in some way, the carbon in them would have gone back to the atmosphere. That's what's been going on the planet for billions of years. And what we're doing using biogenic building products is basically just interrupting that flow. Like, yes, that carbon is going to go back to the atmosphere at some point, but over these, super critical next few decades, if we can keep as much of that out, especially if we can get it up into, millions or tens of millions or hundreds of millions of tons, it makes a big difference. So we're basically trying to lengthen that period of time between the natural cycle where that carbon would have gone back to the atmosphere and sort of put it in a building, which is a pretty safe place to put it, lasts a long time, gets tracked really well once it's into a building, and sort of grow the amount of time that we have before that carbon is returned. One of the questions that I typically get is, well, how much difference does that lifespan make? You know, if we're saying we're going to keep something in a building for 40 years or 60 years or 80 years, like, does that do anything? So there's a type of life cycle assessment called dynamic life cycle assessment, and it's actually trying to do what I just described to you, but in much more detail. It's trying to map the actual climate impact of emissions or withdrawals from the atmosphere. And so what I did here was use this dynamic LCA tool to sort of show 100 years of, or 100 kilograms of carbon, could be in any kind of building product, could be 2x4s or mass timber or an insulation or a carpet or anything like that. You can see that the line sort of goes down. The planet actually gets cooler. So I think, I'll see if this works. So our thing along the left here, that axis is actual degrees Kelvin change in the atmosphere. So things get cooler, and then when we when we dispose of the product and all that carbon goes into the atmosphere, you know, obviously it gets re-emitted and it pops out, and there's actually some warming that happens at the end. But if we had just emitted that 100 kilograms, this diagram would have gone up the same amount that it's currently going down. So you can see the emission later on is a lot less impactful than the emission today. And that's because this is built on an assumption that we're going to do something about climate change, and so 100 years from now, you know, an emission won't be as dramatic or bad a thing as it is currently. And then the second graph shows what happens if we take that same 100 kilograms of material, put it in a building. At the end of 60 years, we do something with it that only allows 20% of it to go back to the atmosphere. So either we bury it deeply, we turn a little bit of it into biochar, you know, or we recycle some of it, but it only takes 80%, it only takes 20% reduction to keep that line. Oop, my thing's going. You can see the line doesn't go back into warming again. So, you know, there is, when these products get to the end of their lifespan, there is an emission, but it's typically not as dramatic as if we emitted it today. The other thing that complicates how we think about these carbon removals is whether we're sort of looking backwards when we're accounting for the carbon storage or looking forwards. And by that I mean, if you look backwards, what you're saying is, especially for a forest product, that tree has been absorbing carbon for the last 30, 40, 50, 60 years before it got harvested and put into my building. But the day I put it into the building, the climate is in the condition it's in. Like, the tree didn't help us, like it got us to where we are, but it's not an additional reduction in emissions. For that, you would want to look forward and go, okay, because I use this wood product, somebody then planted a tree or two, and those new trees are going to grow and absorb carbon over the next 30 to 60 years. So again, LCA doesn't sort of tell you which direction to look in, whether it's more valuable to think about the carbon having been stored and therefore like has value today as storage, or has value sort of going into the future. With other types of biomass, especially annual crops and especially agricultural residues that are where we use things that are already being grown for food, we use the byproducts to put into buildings. Whether you look forwards or backwards hardly matters, because it's, you know, 6 months to a year for those crops to grow. So it doesn't really matter if you're thinking about it, you know, looking back or looking forward. By the time it's in your building, you know, it's stored again in the forward direction, and it's only been, you know, a year since it was taken out of the field. So short cycle crops are actually pretty straightforward to account for because they don't have this really long and difficult time lag to figure out. Timber, on the other hand, is really complicated, and I think a part of the reason that we haven't taken carbon storage in buildings as seriously as we should be is because timber is really the only thing that gets any airtime. It's the product that everybody's talking about, that everybody thinks about, but it's wicked complicated to figure out whether a kilogram of carbon in a wood product in a building made any difference to the climate or not. And that's because when you remove a tree, you're removing a living carbon sink. So the counterfactual is, if you'd left the tree there, it would have gone on sequestering carbon for potentially many decades. So that's one counterfactual. The other is that we only managed to get about half of the total volume of a tree into a building product. The rest is bark and branches and slash and sawdust and like all the stuff that didn't make it there, most of which goes back to the atmosphere really quickly. So if I have 100 kilograms of carbon in a tree and I put 50 in my building and I sent 50 up into the atmosphere, I haven't necessarily done anything good for the climate, even though there is 50 kilograms of carbon stored in my building. But if it took 50 going into the atmosphere to make that happen, again, we don't know. Nobody ever accounts for the root mass. So the 20% of a tree's volume that's below ground never gets counted. So that's another chunk of carbon that stays in the ground, rots, and goes back to the atmosphere. Then you get carbon that's released from the soil as you harvest trees and expose the ground, and erosion happens. And then even if you do replant 2 trees for every tree you cut down, for the first several decades, those trees don't absorb as much carbon as the tree you cut down. Eventually they will, but over the next decade or 2, they're not. So I would never say like building with wood is the wrong thing to do. And I think there are cases, if your forestry practices are well tracked and you're sort of able to account for all of this stuff, that you could say that wood is net carbon storing. But in general, in all of the calculations that I do right now, I don't. I think, I don't have enough certainty that wood is, valuable. It's valuable for lots of other reasons, but as a carbon storage mechanism in buildings, I'm not convinced that we should count it that way. So if you are looking at products and you are trying to assess, any carbon storage value in them, what you want to do is on the EPDs, you just want to make sure that you're really looking for, is this carbon reported? How has it been reported? If I'm comparing 2 different things, are they reporting them in the same way or a different way? And if you want to get really nerdy about it, if they're not reporting it in the same way, you can figure out how to do it so that they can be converted. So biogenic carbon inventory, or GWP biogenic, is something. These are just a couple of snapshots from some EPDs, but that's how it would show up, and it shows up typically as a negative number in the early life scenarios. So I'll show you some case studies now of buildings that use like non-timber products as their carbon storage. This one, Zero House, was a project that I did with the students at the school back in 2017. So it's a little 1,100 square foot residential building, and it has 14 tons of storage in those 1,100 square feet. But what I love about this building, and it's sort of another part of how we can think about buildings as carbon banks long term, is we completely designed this building for disassembly. So we were able to build it at our home base up in Peterborough. We took it down, put it up at a design show here in Toronto, and then took it down and put it up for a client up in Collingwood, all without wasting, wrecking, or needing any more material. So, if you have biogenic materials, everybody's thing is, oh, what's going to happen to it at the end of life? Well, if we're smart about end of life is it gets dismounted here and it gets used over there. It's not typically that these products wear out. It's that we no longer want this building, or the property value changed and somebody wants to do something else on it. So if we can design for disassembly, any carbon we store in the building, can have another life. And then the rest of the case studies are projects that I've gone and visited in Europe, like this one, the De Roomley Sports Hall. It's a retrofit of a community center in the Netherlands, and they wrapped the entire outside of the building with these straw insulated panels, straw and wood fiber board insulated panels, and then used a charred timber as the cladding on the outside. This is a large shopping mall in England, a Marks and Spencer store, And this uses a timber frame and then has these precast hempcrete panels wrapping it on the outside. This is a school in France that uses prefabricated straw bale wall panels as the exterior wall system. Another couple prefab straw bale buildings. One is a library at University of Nottingham, and this one, there's actually a second building to the Jules Ferry residence, but two 6-story, 7-story apartment buildings side by side. The Enterprise Centre in the UK uses these really cool thatched, prefab thatched panels on the outside, and a whole bunch of biogenic materials on the interior of the building too. And I think we tend to not think about interiors, both when we're thinking about embodied carbon emissions, but definitely when we're thinking storage. And there are all kinds of great products that people already put in buildings that are carbon storing. Linoleum flooring is a net carbon storing product. The various types of wood wool soundboards and all kinds of partition wall systems and things like that are carbon storing as well. So we did a study for a renovation of an office in California and showed them that they could store 3 times as much carbon on this interior retrofit as the emissions were for their retrofit. So there's tons of opportunities on interiors. And so right now, what I'm working at RMI is to sort of go deep on the assessment of how much carbon could we put in buildings. Because my focus is sort of low-rise residential, that's where the work is going now. But what we're finding is this is the Department of Energy's sort of prototype home for the U.S. So we use that as the model. And what we're finding is that if we use things like cellulose insulation, egg fiber ceiling boards, compressed straw board wall partitions, bamboo cladding, et cetera, a whole bunch of different products that go into this, that we're able to get about just under 33 tons of storage into a typical sort of 2-story single-family home. And that's, if we'd built the home conventionally, it would have had about 35.7 tons of emissions. So that's a big, that's we're not emitting those emissions, and then we're storing these 32.9 tons. And so what that means is that, if we were able to get, every new home that's built in America, carbon storing to the max, we'd be storing just under 25 million tons of carbon a year in that building stock. To give you a sense of that, all the carbon dioxide removal projects that have happened worldwide to date have added up to 500,000 tons of carbon have been stored. So, just residential building stock, new residential buildings in the U.S., would be the single biggest carbon drawdown that's happened. And you could do the same exercise with, office buildings or high-rise residential, but this is my focus. And so, there's so much that we could do there. And so what are some of these products that we're talking about putting in buildings? Prefabricated straw bale panels are sort of one of the leading options, both here in North America, but in particular in Europe. There's a lot of commercial ventures doing this now. Straw is the stem that's left over when we grow cereal grains, so wheat or oats or barley or rice or rye or any of those things. There's a little seed head that we eat, and then there's a stalk that's like a little mini tree. Typically that gets burned off in the field or tilled under, and it rots back into methane. So prefab straw bale wall panels are a great option. Hemp lime or hempcrete, if you've heard of it. There are a number of companies in Europe, in Europe, that make prefab panels and blocks. For exteriors, lime plaster with cork as the aggregate is a great carbon storing option. There's bamboo cladding. Compressed straw wall boards and ceiling boards get used as partitions a lot, another great option. Eelgrass panels, they're a fire retardant panel for inside buildings. I don't have to read all these. Bamboo flooring, cork flooring. There's just a whole bunch of them. If you start exploring, there's quite a bit in terms, and lots of different insulation products. That's sort of a big category for especially the ag fiber residues. And really interesting things, kind of starting to emerge, not really commercial products yet, but this company, Occam Works, is doing structural mycelium, so able to replace wood with a mycelium that's grown in a bed of sort of agricultural residues. Cyanoskin is making photosynthetic paints, so you paint them onto concrete and the moss grows. And then really exciting, I think, and probably the game changer in terms of how much carbon we can get into buildings is the work that's going on now in the sort of like concrete, cement, and sort of aggregate space, where you have things like Prometheus Materials. They just started up their first CMU plant in Colorado, and their cement is actually grown by algae. So there is no Portland cement in their blocks. It's an algae-based cement. Blue Planet is making aggregate from mechanical CDR, so direct air capture carbon dioxide, and then they recarbonate it into aggregate to put into concrete. Biomason is sort of like Prometheus, but they use microbes to make cement. And lots of interesting stuff going on with sort of lower carbon concretes too, so that you can sort of mix. If you mix Blue Planet aggregate into a conventional low carbon concrete mix, you sort of get towards net carbon storage in the concrete side too. So I'm going to wrap up just by sort of trying to encourage you to be ambitious in your goals when you think about this stuff. I know that there's been lots of this, like I just snipped these because I typed getting to zero into a search engine, and there was literally like, so many people are working on getting to zero. And I appreciate that as a goal because we're nowhere near zero, both on operational or embodied carbon yet. But getting to zero doesn't fix things. Getting to zero just, we stop making a mess, but zero doesn't clean up the mess. Like we stop making more mess. And so I think, what we want to do is think about this in terms of, how do we do more good, not less bad? And in particular, when it comes to the climate, because, the climate curve, if you sort of, the blue line is, our emissions have been going up. We hope they're peaking right now, and we're hoping they're going to get close to zero, 2050, 2060, 2070, everybody's guess is as good as the next one. But even if we do that, even if we get to net zero by 2050, like the best possible case scenario goal, the planet gets warmer for another couple hundred years. Like the emissions that are in the atmosphere now don't magically come out of the atmosphere just because we stop emitting. We just stop emitting, but what's in the atmosphere keeps trapping heat. And the red line there is, the temperature gets hotter and hotter on the planet, even if we get there. And so it's not really enough to just like, okay, we'll stop. It's like we have to actually do something to get the carbon dioxide out of the atmosphere. And hence the name of the book, Build Beyond Zero, is really, trying to encourage us to think about, how can we get there? So the little motto that our team at RMI has come up with is emit less, store more. That's been our go-to motto for the last couple of years as we've been working on this. And there are some resources if you want to dive into this topic in any more depth. There's been some really great work done, and there continues to be really inspiring things happening to get us beyond zero. And that's the presentation, so happy to do Q&A now.
Perfect. So I think we're going to pop the QR code back up on the screen. You should have it for those of you online, and I will be looking for questions coming in. But while we're doing that, if anybody here has any questions, you can raise your hand, and I will shove the microphone in your face.
That just sounds great.
I know, doesn't it? It sounds very exciting. I did have a question, though. With the Rocky Mountain Institute, are there other people doing research on low-carbon multifamily homes or high-rise homes?
Yeah.
So there are other organizations that are looking into the same sort of research, but not yourself?
No, I'm focused on the sort of low-rise. That's where I've spent my whole career. That's what I know best. So, yeah.
This was a really great presentation. I do have a question. Wait, I have to find it. View results. Well, I can announce right now, not announce right now, but for those of you wanting the AIA credits, apparently you will receive a survey link to actually fill that out first, and then sorry, I'm trying to get this. I see that there are questions coming in, but I can't actually get to them, so I apologize. Let me just see. Oh, yeah, go ahead.
You don't have to show me. I just want to know what do you think is the biggest deterrent from us getting to that point? I mean, we all, as practitioners, as architects, we always kind of try to achieve that goal, and that's kind of like we're trying to get to. So what do you think is preventing us from being there?
I would say, it's a pretty typical mix of things. There are a handful of incumbent products that are carbon storing, but most of them are newer or more innovative. So there's all of those hurdles. Where you get them, do they have the right certifications? Have they been tested in your market? All of that kind of stuff. I think still one of the big hurdles is valuing that appropriately. Do your clients come to you wanting a net carbon storing building? Do we actually know what that is? Are we counting wood or are we not counting wood? I think there's a lot to figure out on the technical side too of that. And then, I think a lot of the more innovative products obviously tend to cost slightly more, although not always. And that's one of the things that I'm excited about in the residential market, is that quite often things like a prefabricated straw bale wall panel is actually the same price or sometimes less than conventional. But if not the actual cost, the cost your time as a practitioner, I got to go find this product. I've got to figure it out. It's got specs that I've never worked with before. Like all of that stuff, I think is all of them add up to be inhibitors to exploring it. Yeah.
So we did have one question here. What is the likelihood that other countries around the world will also get to net zero in a similar time frame? That's a big question.
As a non-climate scientist, I don't know. I mean, certainly, my experience in the building world, Europe as a whole is quite far ahead of us here in North America, and in particular, France and the Netherlands and Denmark actually have bio-based building strategies as part of their climate action plans, and they are rewarding builders for achieving lower and lower embodied carbon, and they are valuing stored carbon as part of that. So I think there's lots of great precedents, but I don't think anybody's in danger of reaching zero emissions anytime soon.
There was another one. Sorry, it disappeared. Oh, how can we work with current codes? I'd love to use eelgrass on school projects, but would need to meet certain criteria.
Yeah, so it's going to depend where you're doing that. So the eelgrass panels, they're a European product. They have all of their, fire and all of those kind of certifications for those markets. But I know, having in my practice been involved in sometimes bringing things over, that doesn't always translate, here in Canada or the US. So it would be figuring out what fire standards did it get tested to? Is there a ASTM or whatever equivalent here? All of those kind of questions. Yeah.
So another hurdle.
Another hurdle. Yeah. Yeah.
Do you know if there are any hospitals that were built with straw bales?
I don't know of any hospitals with straw bales. I do know that there have been some hospitals. There's a Dura. It makes the compressed wall boards that I was showing, and they've done a lot of hospital ceilings. So it has been. That's the only product I know, straw-based product, that I've seen used in a hospital.
Can you talk a little about how forestry stewardship practices impact this topic?
Yes. And we could do the 1 minute answer or the 3 hour answer.
You've got 13 minutes.
Yeah. I mean, it's an interesting one. Right now, none of the forestry standards directly measure carbon flows. There are a bunch of things in them that are good proxies for that. So like FSC, takes really good care to minimize erosion, and carbon coming out of the soil from erosion after harvesting is one of the big emissions that happens. But we don't know how much an FSC forest emits from erosion. We just know it's probably less than other ones. So I think both SFI and FSC are working on more carbon-related actual metrics, but right now it's sort of, people kind of take them as this is better wood and potentially better for the climate, but there isn't actually any science that says yes, like this, you have done something better for the climate by using wood harvested to this standard.
So more research.
Yeah, more research. Yeah, I think another thing is that there is a lot of wood that can come out of forests and is coming out of forests. Things like thinnings, when you're trying to avoid forest fires. Right. Quite often the Forest Service will go in and do huge amounts of thinnings. That wood just tends to sit. Like, you cut it down, you pile it up, and you either burn it off or you let it rot off, but you take it out of the forest. So being able to use wood like that that's already being cut down kind of takes out one of those counterfactuals of like, what would have happened to this wood? Well, we had to cut it down anyway to prevent forest fires. So if you can source wood products that are using that kind of wood rather than timber that was just harvested just to be timber, that's probably I would say in that case, I would count carbon storage in wood like that.
Right.
Yeah.
So what sort of policies do you think will be most effective for driving adoption of these biogenic materials?
I think making sure that as embodied carbon measurement becomes more common at the sort of federal, state, city, province levels, that there are rules sort of requiring measuring biogenic carbon so that it shows up in the same way, so that everybody is starting to see those numbers and use them the right way, and then making sure that those programs value that stored carbon. So, for example, the City of Vancouver's residential program, you do your life cycle assessment, but the negative number for biogenic products counts in your score. So if you want to get, I think they're offering up to $40,000 per home for a really low embodied carbon score. So clearly the way to get there is to put as much carbon storing material in that building as you can. So I think making sure that shows up in programs makes a big difference.
What resources would you recommend for designers to find the products you mentioned?
The best one right now, and again, it's not just a European thing, but its focus is there's a website called 2050 Materials. They have a really great database they've sort of made a focus, and you can actually sort by biogenic in a bunch of different categories, and they if there is an EPD that shows carbon storage, they'll have that information there. So that's
the best
a good go-to. Yeah.
What are immediate actions we can take to influence our policymakers, either in the government or in industry organizations like the ICC or the AIA?
Yeah, that's interesting. I mean, here in Canada, the federal government's committed to having embodied carbon in our building codes by 2030. So I would say, for people in this office, following that, when public comment comes out for how they're going to handle that, like comment and sort of make sure that the carbon storage is counted in there. A few different, in the US, like there's been a few things before the International Code Council on this. They haven't taken it up. They haven't taken up embodied carbon at all yet, not just biogenic, but embodied carbon, partly because there's a bit of a, nobody's quite sure where it lives in codes because it's not a life safety issue. And then, it kind of got booted over to the energy codes, and the energy codes people are like, but it's not an energy thing, it's an emissions thing. And so right now it has to find a place to live, but it is getting there. ASHRAE has their new 240p standard. It's gone out for one round of public comment, and that'll be really important because there will be an ASHRAE standard for tracking it, and I think a lot of codes will reference that. So I think that's a good one to look out for.
Yeah. And I think that's it. That's all we have for questions.
Okay.
And we're pretty much right on time.
Great.
So thank you, Chris.
Excellent. Yeah,
Really
thanks.
appreciate it.
Yeah.
Really awesome
Yeah.
presentation. And again, you will receive a survey at the end. Fill that out if you want your AIA credit. And thank you, everybody. Thank you, everybody from the World Wide Web. Thanks, guys.
Thanks, everyone.